Hello everyone. I hope that this will work right now and we can jump into programming. C programming. So what do we have this time? Let's see that. C. Okay, as for now, what I see here and also you see is that we move on from chapter 1 to chapter 2. So we finished with running Hello World, and now we move on to understanding program structures. Is that correct? Yes, it is. So let's jump in. The following topics we will cover this time: understanding the building blocks of programs, statements, and blocks, introducing the various kinds of C statements, understanding delimiters, using white space to make your program easier to read for humans, introducing functions and their parts like parameters, and learning how a computer reads a C program as it runs, creating various kinds of functions with parameters and return values, and then the last but not least, learning how to declare a function for use anywhere in the source code. A C program, as in most programming languages, consists of a sequence of small individual pieces of computer work called statements, which are formed into larger building blocks called functions, which are then compiled into a single program. As we examine these programming elements, we will expand on the main function, which we encountered already in the running of Hello World. Now, programming languages, as you see, we differentiate between many of them: high-level, low-level, and mid-level languages. Do you also see that high-level languages are the easiest to read, using words and phrases found in human languages? Low-level language are the most cryptic, often containing few, if any, recognizable human language words. These languages, such as assembly, access hardware directly and therefore are extremely fast. Now, of course, the drawback is that development time is slow because pretty much everything must be done from scratch. About mid-level languages, we know that they combine aspects from both high and low-level languages. As such, these languages are quite versatile, and the programs can be designed to do just about anything. C is the prime example of a mid-level programming language. So let's check again. Let's return to the various uses of punctuation that we encountered in our Hello World program. Here is the program one more time. You see, and at first, I'd like to draw your attention to the paired punctuation, the punctuation that occurs with a beginning mark and a very similar ending mark. Going through it line by line, we see the following pairs: opening, closing, opening, closing, curved, opening, and curved, closing. Also, here, opening, closing. So again, we also see some of other punctuation that may not be familiar to you for example, space or new line. There are punctuation marks that are significant in the C language. When we look closely at our Hello World greeting, we can see the beginning character quote mark and the end character quote mark. So everything between them is part of what we will print out to the console, and therefore are two punctuation marks that we can basically ignore. We can ignore the comma and the exclamation point contained between these two quote marks because, as we have already seen, these are printed out to the screen as a part of the greeting. The characters between the two quote marks represent a sequence of characters that is a string to be displayed on the console. Yet, the backslash or backward slash is a punctuation mark that has specific significance when part of a string. Note on your keyboard the location of two different punctuation marks, forward slash and backward slash. As you read from left to right, the forward slash falls forward while the backward slash falls backward, hence their names as well. They have different uses in C. As we have seen with C++ start command, two forward slashes, so characters, constitute the beginning of a command, terminated by the new line character. We will come back to the new line in a short. However, if any other character occurs between the two forward slashes, then we do not have a C++ style command. We have something else, a digraph. In C is a two-character sequence, which means something more than either a character alone. Care must be exercised to ensure that the digraph or digraph of two forward slashes is preserved. Otherwise, the compiler will interpret this as something other than a C++ style command. So in our greeting string, we can see backslash or backward slash n. So backslash n digraph, which represents the new line character to be output to the console. We must distinguish between the new line character, so backslash n digraph, from the carriage return character, which is backslash r. Backslash r is used on some versions of Unix, yet on others both backslash r, backslash n are used together on Windows. These digraphs are intended to reflect the operation of manual typewriters. Manual typewriters have a carriage with a rotating platter and return lever. Ding! Right? Remember? When the return lever is manipulated, it first rotates the platter, giving a line feed or a new line. Then the lever is forcibly pushed to the left and the carriage is returned to the beginning position. That's why we call it carriage return. Most often, these two actions are combined into one swift and firm movement, new line at carriage return. Let's do an experiment. What happens on your system when you replace on with R? So \n with \r. The most likely result is that it will appear as if no greeting was printed at all. If that is the case, that actually happened as a text printing focus went back to the beginning of the line, but the line was not advanced. The console prompt wrote over it, wiping out your greeting. If you want to advance to the next line without returning to the beginning of the line, you should use line feed character \v. Let's try it. Perhaps this time in dev. So let's create the first file, which we already have done. Again, include stdioh, and we continue with int main and a curve bracket and printf hello world and \n semicolon return 0 semicolon I said. Oops, where is it? Yep. Hopefully this time it works and I didn't make any mistake. Let's save this as hello to C, and let's try to run it with F11 and let's see the result. We got hello world. Okay, now I replace R with R. I recompile and rerun it. I got this here. And also let's see what we get as a result. And also let's see if that would be our case if I run it. With GCC on CMD. So Control R, CMD. I have to move to my folder first. Now that I'm there, I can show it to you. So there it is. And let's see if this time it would work fine. GCC hello to CO. So compile it into hello to exec and hello to C I said, right? So let's try to run it. Good. Hello to, and let's see what we get this time. Hello world. Okay, what if I, so let's save it again. Okay, no problem. So it returns exactly what we wanted. What if I do another line here, print f, good, bye. Take the next line again, so new line, and let's try to run it with semicolon obviously. So let's try to run it. And what I get is going to be very strange this time. So I'm going to do this again here, that you see. And this is what I get. Goodbye. The reason is because actually, as you remember, we started to delete everything because we did not take the new line. We just basically moved with the R, so the carriage return. So we returned to the beginning here, yet we just overwrite the hello W part because it's 1, 2, 3, 4, 5, 6, 7, 8, 9 characters. So 1, 2, 3, 4, 5, 6, 7, 8, 9 characters. So the goodbye will overwrite the hello world and will be taking the place from the hello world up to the RLD characters. Okay, now that we have already checked that, we can continue and moving with other parts as well. Let's see some digraphs here. Okay, now digraphs that appear in strings are also called escape sequences because they escape from the normal meaning of each single character. They all begin with a backslash character, and the following table here, as you see, shows the legal C digraphs. So alert, backspace, form feed, new line, carriage return, horizontal tab, V as vertical tab, and single quote, etc., etc. Now let's see the following situation here. Let's take V instead of R. Let's save this and let's rerun it. Press F11 and you see what I got. Hello world, goodbye. So everything is fine. But again, V stands for line feed. Okay. Moving forward, we have single quote, double quote, question mark, and backslash itself. Now let's try to use this text in our file. Let's create that newly. Again, so here we go. Include stdio h. Then the next one is int main. And print f hello. Why I don't get, okay, hello world. So without a new line, what I'm going to do is that I get a space there additionally, just to make sure that my next hello world is separated from that. Hello world with a new line this time. So backslash n, then print f again, print f a string quoted text inside of it, and let's add also the new line again, print f, and this time tabbed. So backslash T column backslash T headings. As for now, we need another new line. Again, printf, and all of them must be again semicolons. A line of text that spans, so backslash n spans 3 lines, and backslash n and completes the line, backslash n again, begin and again, closing, and now I have it, and now I want to close it. Perhaps we could add return 0 for just in case, and now this should work. We could add also the following, so end of file, just as usually. Save. Now let's try to do it. So gcc text format c again -o df exe, and I have some other problems here. Let's see what we have here. So missing termination. Let's see what it is. So you see here, basically, this is it, where I made a mistake and I didn't use a quote mark. Hopefully this time it runs well. Yep. And tf, and let's try to run it. Should run. Perfectly done. Okay, such mistakes can also happen with me, so not only with you. Now, next one is, as you see, we have here a little bit more text to do. We will continue with our text file here. You can use it not only here. If you want, obviously you can put it into an online C compiler. You see one of them here. You can use other online compilers as well, it doesn't matter. So let's try to run it this time, and you see the text the same, what we get and what we actually had as well. Good. As for now, let's do int main and just add this time the following situation. Here we go, and you can also do the same I do, just simply copy paste your code inside and use it. The parts you already know, so just save it, and let's try to run it again. And hopefully there's no problem, and I can run it well. This is it. This is actually what I wanted. I got it well. So, okay, now this program is a series of printf statements that each writes a string to the console. Note that the use of the new line character, so \n, that typically appears at the end of a string but can appear anywhere in it or not at all. The third string, an escape sequence \, is used to print the character quote mark in the output string. Notice, tabs, so \t can be embedded into any string. When you have typed in this program, saved it, you have the following output. Okay, what if I do add here, as the book actually adds already here, the void? It doesn't make any issues yet, and we will talk about that later on. So, but first, now continue with understanding delimiters. Delimiters are characters used to separate smaller parts of the program from one another. These small parts are called tokens. A token is the smallest complete C language element. A token is either a single character or a sequence of characters predefined by the C language, such as int or return, or a sequence of characters, words defined by us, so defined by you, which we will then also learn about later. When a token is predefined by C, it cannot be used except in a prescribed way. So the way of the use is previously decided, determined. Those tokens are called keywords. For keywords we have already encountered include int, main, and return. We will still see many other throughout the course. Now there are three types of delimiters that we will explore here. Single delimiter, so backslash also, but semicolon or space. Paired symmetric delimiters, you see them here. Asymmetric delimiters that begin with one character and end with another one. Each of these has a specific use. Most of them have unique, unambiguous use. That is, when you see them, they can mean one thing and only that one single thing. Others have slightly different meanings when they appear in different contexts. In our Hello World program, there are only two required space characters that are delimiters. We see a delimiting space here between int and main, and we also see a delimiting space between return and the 0 value. In these cases, the space character is used to separate one keyword or token from another. A keyword is a predefined word that has a specific meaning. It is reserved because it cannot be used elsewhere for some other meaning or purpose. int, main, function, and return are all keywords and tokens. 0 and semicolon are tokens. One is a literal value and the other is a delimiter. The compiler identifies and translates tokens into machine language. As appropriate. Delimiters, including space, facilitate interpreting text in the program compilation stream into tokens. Otherwise, when spaces are not needed to separate tokens, they are optional and are considered as white space. you can see the paired symmetric delimiters from the list of types of delimiters. One always begins a particular sequence and the other always ends it. So you see here, this one is used for the specific type of file name, which tells the compiler how to search for the given file. The next is parenthesis, indicates that the token is associated with a function name, and the next is the curly bracket that indicates a block that groups one or more statements together into a single unit. We will explore that statement again. Finally, we have the quote mark, indicates that the beginning and the end of the sequence of characters also referred to as a string. Now we also consider the first line that starts with sharp and ends with a new line. This is an asymmetric delimiter pair. This particular line is the preprocessor directive. So don't forget, this is the preprocessor directive. The preprocessor is the very first part of the compiler phase where directives are interpreted. In this case, the file name stdio.h is searched and inserted into the program compilation stream, or included, just as if the file had been typed into our program. To direct the compiler to insert it, we only need to specify its file name. The compiler has a predefined set of locations to look for it. The compiler finds it and opens and reads it into the stream. If it can't find, an error is reported. Now, this sharp include mechanism allows a single file to be used instead of manually copying the contents of this file into each and every source file that needs it. If the stdio.h file changes, all programs that use it can simply be recompiled to pick up the new changes. Otherwise, any changes to any version of the copied text of stdio.h would have to also be in every file that also copied its contents directly. Too much complicated. So that's why I use just simply sharp include. We will encounter many of these kind of files, those that are part of the standard library and those we create by ourselves, as we begin to make our programs more complex and useful. Now, with our understanding of delimiters, we can remove the extraneous spaces, tabs, and new lines. We can pare it down to just keywords, tokens, and delimiters. Our program, hello new white space C, would look like this. You see that? And that also would run the same way like we have just run it before. Now, is it a good programming practice? Obviously not. Never. You might think that a practice like this would somehow save space on your computer's hard drive or SSD. In the reality, the space saving is insignificant, especially when compared to the added human time needed to understand and modify such a program. It is a basic fact of programming that programs are read many times more often than they are created or modified. In reality, every line of code is read at least 20 times over its lifetime. You may find that you reread your own program several times before you consider changing them or even reusing them. Others will read your programs with or without your knowledge. Therefore, while we pay attention to the rules of the compiler and strive to write complete and correct programs, we also strive to write clear programs for other humans to understand. This not only means using commands effectively, but also using white space effectively. Now, note that we do not remove the space in our string message, right? Okay. So when a space or new line character is not required to delimit a portion of C code, it is considered white space, and white space can also be tab, carriage return, and some other obscure characters. However, the use of tabs in C source files is discouraged since the program listing may look different on someone else's computer or when the source code is printed, thereby diminishing clarity and obfuscating your original intent. There you go. Now, always use spaces instead of tabs in your source code files. There are many options by as many programmers on how to effectively use white space. Some programmers feel strongly about using two spaces to indent a line, while others are vehement about using four spaces. Others don't care one way or the other. In reality, there is no one correct way to do it. As you write more of your own programs and read those of others, you should pay attention to white space styles to try to get a sense of what is effective and what you might prefer by yourself. Consistency in code formatting, including white space, is more important than you might think. Consistent code helps set the code reader's expectations, making the code easier to read and hence to comprehend. Inconsistent white space formatting can make the code harder to read and consequently introduce coding errors and bugs. Here is an error example. So here is an example, and it does the same hello world, but yeah, it's really nonsensical and inconsistent. Note that this is still the valid C program we had before. It will compile and run and provide the same output, so hello world, as before. The C compiler ignores the white spaces. Because this is an example of bad practice, you do not have to type this in yourself. In the remaining programs, here, all source code will be presented with both consistent white space usage as well as a consistent commenting style. You don't have to adapt these stylistic guidelines, but you should pay attention to them and compare them to other styles. Whatever style you choose, apply it consistently in your own code. Okay, now here's a table of delimiters that we have already encountered in our simple program. Curly bracket, angle bracket, hash, okay, double forward slashes, new line, So again, angle bracket, hash, and also double quotation mark. Now, we will see later that some of these punctuation marks have different meanings when used in different contexts. When their use is not as delimiter, the alternate meaning will be clear from the context. For instance, an angle bracket opening is the less than logical operator and will occur alone when it has the meaning. So for completeness, we have included the delimiters to indicate an array, which is a square bracket. Okay, and we can continue with introducing statements. Statements in C are the basic building blocks of programs. Each statement forms a complete unit of computational logic. There are many types of statements, and they are made up of wide variety of elements. Simple statement, as you see here, is for example return 0 semicolon. Block statement begins always with a curved bracket and also closes with a curved bracket. They contain a group of other statements. Here we represent them as this: curved bracket open and then curved bracket closed. We represent one or more statements of any type of valid statement. The next one is complex statement. This consists of a keyword and one or more block statements, like main, which is a complex statement. It has the main keyword and other predefined elements, including a block statement. Compound statement. These are made up of simple statements and all complex statements that consist of multiple statements. The body of our program is a compound block statement that consists of two statements: a call to printf function and the return 0 statement. In our Hello World program, the following are the kinds of statements we have already seen. Now, in our Hello World program, the following are the kinds of statements we have already encountered, as I mentioned. Preprocessor directive. So this begins with the hash and ends with new line, or sharp and ends with new line. It isn't really a C statement that performs computation instead. It is a command to the compiler to process our C file in a specified way. Preprocessor directives do not follow C syntax and formatting, but they are included in the language. We can think of them as outside of C syntax. They direct the compiler to do extra preparatory stuff before the compiler gets down to the actual work of compiling the program. So, preprocessor directive. Function statements. The main function, which is where our program begins executing, is really predefined. So it's a predefined name for a more general function statement. By adding statements to main function, we define our program. Every executable C program must have one and only one main function defined. It is a complex statement. We will also define our own function statements, or more simply stated, our own functions. Function call statement. This is a simple statement, just as main function is called by the system to execute, we can call functions that have already been defined or that are defined in our programs. In this case, we call the predefined printf function to do some of the work for us. When we call a function execution of the current statement of the current function is suspended and the execution jumps into the called function and continues in that function. Return statement. This is a simple statement that causes execution in the current function to end. Execution that then returns to the caller. In the main function, when return is encountered, our program ends and control returns to the system. The next one is the block statement. It's a compound statement that consists of one or more statements enclosed in curved brackets. Block statements are required for function statements and control statements. We will call these named blocks and have a well-defined structure. Yet, we can also group statements together into unnamed blocks to organize multiple statements into related units of computation. Unnamed blocks have a simple structure and can appear anywhere that a statement can appear. For completeness, here are other statement types that we will encounter later on. Control statement is the following. This includes if, curved brackets, else, curved brackets, or go to and break and continue. These are control statements. The return statement is also a control statement, like a call statement function. These change the order of execution of statements within a function. Each has a well-defined structure. Looping statements. These include while, do, while, and for. They are similar to control statements, but their primary purpose is to iterate, that is, to perform a statement 0 or more times. We will look at this later on. Expression statements we will also look at later. These are simple statements that evaluate expressions and return some kind of result or value. Except for control looping and the wide variety of expression statements, we have already encountered the essential C program statements that make up the bulk of our C programs. Let's look more for more. Introducing functions. Now, functions are callable segments of program code that perform one or more statements of related computational work. Functions group statements into a cohesive set of instructions that perform a specific complex task. This may comprise a single statement, only a few statements, or many statements. Functions can also call other functions. Functions made up of one or more statements are the next higher up, more complex units of a program composition. Statements make functions, functions make programs. Indeed, the main function is a function made of statements and other functions. The process of writing programs, or also solving a given program with computer program, is primarily the task of breaking the problem down into smaller pieces, so into functions, and focusing on the work to be done in each smaller piece. When we break a problem down into smaller parts, we can more easily see the essence of the problem. We can focus our attention either on aspects of the larger problem or on the fine details of subdivided problem pieces. We may be able to reuse a single problem piece or function so that we don't have to copy and paste it throughout the program whenever it is needed again. Anytime a function changes, we change it in only one place. If we discover that a function does not cover all the cases we originally expected, we can either expand its functionality or add a similar function to provide a slightly different solution, or further break the function down into smaller functions. Now, this approach is preferable to writing one large program without any functions. In many cases, writing a monolithic large programs without functions can and has been done. However, each time a program like this would require modification, it would have to be understood in toto, so that even a small change might require the entire program to be considered. When the problem can be expressed so that we can see its major and minor parts as implemented in the functions, it's most often easier to understand it generally, and its components easier to modify. So, understanding function definition is the next level here. Functions, therefore, are essential to part of any C program, and each function that you will create has the following parts. You see here function identifier. This is the name of the function. The name of the function should match closely to what it actually does. As for the next one, function result type or return value type. Functions can return a value to the caller. The caller may ignore the result. If the return value type is specified, the function must return a value of the type of to the caller. Function block. A function block is a block directly associated with the function name and parameter list where additional statements are added to perform the work of the function. Return statement. The primary mechanism to return a value of the specific type from the called function to its caller. Function parameter list is an optional list of values that are passed into the function, which it may use as a part of its calculation. Now, the goal is for you to begin to recognize, understand, and be able to create a function statement pattern for yourself. We will use an absolute minimum C program with main as our example function and highlight each essential part afterwards. A function type, function identifier, and a function parameter list comprise the function signature. So once again, function signature is made of function type, function identifier, and function parameter list. In a C program, each function identifier must be unique. In other languages, the complete function signature is considered, but not in C. When a function is called, only its function identifier is considered. That is the name. Once the function has been defined with a function identifier, that function identifier cannot be redefined with a different function result type or function parameter list. Each function identifier must be unique in C. Note that the function signatures are not used in C to uniquely identify a function. Therefore, two functions with the same identifier but the different parameter list or result types will cause a compilation to fail. As for the next, exploring function identifiers. So main is a function just like any other function. However, it does have some significant differences. The main function identifier is reserved. The signature for it is also predefined in two specific ways. So you cannot name any function in your program as main, and you can never call main itself. Main can only be called by the system. Function identifiers should be descriptive of their purpose. You would expect a function named print greeting to print greeting. Well, we already talked about that. Function identifiers are case sensitive. This means that lowercase main and uppercase main and sentence case main are different function names. And when two functions have a similar purpose but are slightly different, do not rely on differences in the upper lower case of their names to differentiate them. It is far better to make them slightly different in length or use different modifiers in their name. Two common methods to make function name descriptive yet easy to read is the camel case and the underscore separated, and also known as snake case. Camel case names have the beginning characters of words with the name capitalized. In underscore separated names, underscore is used between the words. So here you have it. All lowercase, so make light green, make medium green, and so on. Camel case, make light green, make medium green. This is it. And this snake case, the underscore separated. You see that as well. As you see, the all lowercase names are somewhat difficult to read. However, these are not nearly as difficult to read as all uppercase names. So please don't use all uppercase names. The other two ways are quite a bit easier to read, therefore it is better to use either of the last two. If you choose one identifier naming convention, stick to it through your program, so don't change. So if you make all lowercase, then completely take only all lowercase in your program. Do not mix different identifier naming schemes, as this makes remembering the exact name of the function identifier as well as the other identifiers much more difficult and error prone. Now, if you explore the function block is where the work of the function actually happens. Within the function block are one or more statements, as you see here as well. Main in the hello world main function, there are only two statements. Main basically and the return statements. While there is no ideal size, large or small, for the number of statements in function block, typically functions that are no longer than either the number of lines in a terminal, so 25 blocks, or printed page, say 60 lines, are preferable to much longer functions. Okay, so make your function relatively short. In some cases, longer functions are warranted. Rarely, if ever, are they considered good programming practice. Okay, so not at all. Now, as for next one, exploring function return values. A function statement can return a value to its caller. It does so from within its function block. The caller is not required to use the return value, and can ignore it. Hello world, the printf function call actually does return a value, but we will ignore it. When a function statement is specified with a return type, then it must return the value of the type. So, such a specification consists of two parts: the return type of the function given before the name of the function, and the return value, which is of the same type as the return type. In main C or int, short for integer or whole number, is the type specified that the main function must return to its caller. Immediately before the closing brace, we find the return 0 statement, which returns a 0 integer value. In most OS calls, a return value of 0 by convention typically means no error is encountered during compiling a file. If the return type of a function is void instead of int or some other type, there is no return value. The return statement is optional. Consider the following two functions. Here you see void, and there is no return value. Now, in the following program, hello2 C return is expressed explicitly. Let's see that. Let's try to shape our file accordingly. So we will do void print comma and print f comma semicolon and return semicolon, and we've got it. Now what we do here in main, print f hello, then we continue print comma, and then here we do world, and here I need to change it to add the space as well, and I think we are done. So this time I'm taking this as hello to C. So let's save it. And let's hope that it runs well. Yeah, I got it. Here you got it. So it runs well. I also can make a check on my CMD if that would work correctly. Hello to C and hello to exe, and now let's do hello to. Should work fine. No problem happened, so we can return to our presentation. So in the hello2C program, we have a function whose purpose is only to print a comma and space to the console. Type out this program, so just as I did, compile, run, and verify it. Verification should be familiar now, since we are creating the same output. Clearly, by itself, this is not particularly useful function. Yet, our intent is to focus on moving from a single statement in our original Hello World program to a program that employs a number of functions to do the same thing. In each case, the output will be the same. And as we expand our knowledge of C, our functions will become more useful and more relevant in the future. A recent development in C is that return 0 semicolon is optional. If there is no return semicolon or no return 0 semicolon statement, then the value of 0 is assumed to be returned by the function. This, by convention, means everything is executed normally and all is well. With this in mind, the modern minimal main function now becomes like int main parenthesis curved bracket, and return is not necessary. It became optional. The previous main function becomes as following. Yeah, you see that? And then we can continue now with the passing in values with function parameters. A function can be values given as input to the function. It can then use them within the function body. When the function is defined, the type and the number of parameters that can be passed in or received by the functions are specified. When the function is called, the values of the parameters are given. The function call parameters must match the type and number of parameters specified. In other words, the function signature must match both the caller of the function and the called function. So here you are. In other words, the function signature must match both the caller of the function and the called function. Okay. Now we have already seen a printf. Yeah. Okay. And then function parameters are specified in the function definition between the two parentheses delimiters. The ellipses indicate that there can be 0 or more function parameters in the parameter list, separated by commas. A C token we haven't yet encountered, so the comma itself. When there are no parameters, the definition look like here: void, or shorthand just point void, and the parentheses and are equivalent to empty parameter lists. And now each parameter consists of two parts: a data type and an identifier. The data type specifies what kind of value is being used: a whole number, a decimal number, a string, and so on. And the identifier is the name used to access that value. Multiple parameters are separated by a comma. We will explore data types fully later on. Value identifiers are very similar to function identifier, where a function name can be called from somewhere. The parameter identifier is the name by which the passed in value can be accessed within the function body. Yep, within the function body. Okay, now let's look at what parameter lists look like with 0, 1, or 2 parameters. So 0, 1, or 2 parameters. Take as given for the moment that the C type of the string passed into the function is char star. This will be later on introduced. Okay, within the function body, the parameter can not only be accessed but can also be manipulated. Any such manipulations on a parameter value are only valid within the function body again. Once the function body ends, the parameter values are discarded. In the following program, we can see how to use the parameter values within the function body. Here you see. And in the next one, now these two functions, so we can use again. Here we go, sorry. Oops, yeah. So now with these two functions which we have here, we can use them to build a more general greeting function that takes a greeting and the addressee. We also could then call this function with two values, one value for the greeting and the other for who it is being greeted. So first, let's actually create this hello3 file. That is, we change this. I take the content, I make a new file, and I just simply copy paste it first. Then void here, and void. We continue with void print word star word. Let's hope that it would work. Fine. Print. Oops, where is it? Word and semicolon. And now we use here print word hello. Word hello. Then print comma. And print word world. And as for the last one, print f. Exclamation mark and backward slash n and semicolon, and we're supposed to be alright. This time I'm going to save it under hello 3. Hello 3.c, and let's see if that would work correctly. And here we have a problem. Let's see what's that. I believe it's a return. Let's try to run it. No. So I myself did not recover what the problem was, so I completely rewrote the entire program. Once again, let's do it together as well. If that can happen, that can happen. Let's see what's wrong. So let me check. It's immediately. So here we are. I had actually here void. Let's try to run it as well. With void, also runs well, no problem. So with or without void, it runs well. Okay, now let's try to repeat it, and let's see what's wrong. As I said, so void print comma. You can add the void if you want. You don't need to, and then printf. And please enter a comma and then a space, and that's it for this program. Actually, you can copy paste this part make the next print. So print word, and this time you add car, star, and word, and you continue with printf, and this time you have to change this to s, and a comma word, and you're done. You can continue with the int main. So print word, this time hello, and semicolon to the end, then print comma, nothing, void is it, right? Then the next one is again print word, but this time you use world and print f. As you remember, we had the exclamation mark and n, and then basically here semicolon and return 0 semicolon. Now let's try to run it, and there is no mistake this time. It works fine. As I said, I don't know why it didn't work fine. It works no problem, no serious problem, and I guess it would work also under our GCC. So let's take a look. Hello 3, whether it works fine, and yes, it does work fine. So we can continue our work with the slides. Okay, in the two functions defined because the return type is void and the return statement is optional or omitted, we can continue now. As I mentioned, let's do the following. This is now this time hello 4C, and we have much more to do. Let's also do that as it says here in our explanation. Okay, so the next code, what I need to do is void print greeting, and here car greeting car address C. We continue with the next. So print word greeting then semicolon, print comma, oops, semicolon, and again print word, this time address C. Okay, should be fine, and we got our print f here, which we take here this time. Oh, so good. And now let's do work on the main, and let's see what we have here. So int main, print greeting, take this here and use hello comma world. Then as for the next one, print greeting again, good day, your Royal Highness, your Royal Highness. Then next one, again print greeting, we continue. Howdy, Joan, Q, and sorry, Q and Jane P. Dowie. The next sprint greeting goes like this. Hey, Moe, Larry, and Joey. We get rid of this here, and let's see if that would work again. So save as this time, and we turn to hello 4 this time. Saved, so let's try to run it, and hopefully it works without any mistake. And voila, this is what we get. That should be okay. Let's also check here if we have done our work fine. Then hello 4 would be okay. And yes, you see it works fine. No mistakes, no problems are reported. Okay, so passing values in with function parameters, we still continue. Wow, that's a hard job this time, but not much more to do. Now, we have moved the statement from the body to of main into a newly declared function print greeting. You have seen that, which takes 2 parameters of a string type. We have a function that can be called with different values, which we saw in the main body. So print greeting was a function. It's called 4 times, each time with 2 different string parameters. Right? Yeah, and this program can be also made more simple. And the simplification goes in the way that we get rid of a few functions, and we create this print greeting in a different way. So let's see that. Let's take this out. This print word, print comma, we don't need them. So for the next, what we need, we saw here, right? So let's get back here. Who, right? And let's create it. Who, and all these things disappeared this time, and we just have print f the following. So as, so string, one more time, string value and the new line, and then comma greeting who, and the semicolon. Int main should be okay. It says, however, this time let's do greetings, and howdy is fine, but here hey, Mo, Larry, and Curly should be okay. Hopefully it works fine. Let's check it. Now this time also we got it correctly. As for now, let's move to the next as well here. And I'm doing here hello 5 C and hello 5 exe and hello 5 I tried to run. No problem reported, so we can assume that the compiler made the job very well and I did not make any mistake. Now this program is simpler than before. It defines only one function instead of 3, yet it still provides a general way to print various greetings via function parameters. Once you saved it, you can compile it, you can run it. And then again here we can copy hello 5 content into hello 6. Let's create the hello 6 and let's try to check it. Void. Now what we do is the following. We may find that we need to break print greeting into even smaller functions. So the more smaller functions to print a greeting. The advantage of this is to be able to reuse our functions without having to copy one or more statements. So for instance, we could expand our program to not just print a greeting, but also print a variety of sentences, question, a normal sentence, and so on. An approach such as this might be appropriate for the program that processes language and generates text. So what I need now, let's continue here. Okay, let's see. As for the first is void a greeting. And I'm changing this to a single parameter. So this one I need to change as well. I'm all good. Then we need void print comma. This is good as well. We don't need the return here. We need, however, the closing. Okay, then for the next one, void print an address C char and name and print. So basically I need this here with a name. Then as for the next one, print a new line. We can just copy paste this one here, print a new line, and nothing is needed, just the way how we print a new line, no parameter included, so we are done. Then the next one is void print greeting char a greeting char name. Continue with the curly bracket and print a greeting. We call the function and use a greeting parameter in it. Then print a comma. Then print an address C and name. Okay, good. Then again, semicolon. Please don't forget the semicolons all the time. Print a new line, again the parenthesis and semicolon. Once done, then we take print greeting, this function, the void function here, and then hi Bob, and all the others we get rid of because we just need one instance to show. Hopefully this time it works. I tried to save it as hello 6c, and I again have one mistake, and I will check this and then return to you. We have a name problem. We have a print egg comma, and that's why this mistake has happened. Hopefully this time it works fine, and we got a hi Bob. Oh yeah, good job. We got a hi Bob. That was the only mistake this time. Good. You see, before that I already had some other mistakes. Hello 6, and let's run, and this time it runs well. Good, perfect, all good. And now actually I can move on again with the next part. It's order of execution. Let's see what it is about. So in the hello 6c there are more smaller functions to print a greeting. The advantage I mentioned already, and then an approach such as this might be appropriate again when we process language or general text. That might seem like a lot of functions just to print 2 words. However, as you can see, we are able to organize our program in many ways with many functions. We can create fewer, possibly larger or more general functions, or decide to use more, possibly smaller, more specific functions. We can break functions into one or more other functions and call them as needed. All of these approaches will depend on the problem to be solved. So while there are many different ways to organize a program, there is rarely a single way. You may be wondering why we define our functions with specific numbers of parameters, and yet the printf function can take multiple parameters. This is called the variadic function. C provides mechanism to do so. We will not explore this. We will, however, talk about it later on. Okay. Now, in our explanation, to differentiate the function from some other program element, we will refer to the function with the name and parentheses, and the parentheses after the identifier to indicate its function, so where name is the name of function. As means to re-up. Okay, now we can continue with the order of execution. When a program executes, it first finds main and begins executing statements in the main function block. Whenever a function call statement is encountered, a number of actions occur. So, if there is or there are function parameters, the actual values found in the function call statement are assigned to the function parameter names. Program execution jumps to the function and begins executing statements in that specific function block. Number 3, execution continues until either a return statement is encountered or to the end of the block is encountered. So the closing curly bracket. Execution jumps back or returns to the calling function and resumes from that point. Now if in step 2 That is, the program execution jumps to that function and begins executing statements in that function. Execution encounters another function call statement. The steps are repeated. And the following diagram illustrates a call return order of execution when function calls are encountered. This order of execution cannot be violated, since it is very bad practice to jump from within one function to another. C doesn't also allow this. Now the following steps are here are the executions. You see the program is called by the system and begins the execution with the main. The main calls the print greeting, right? If you return to your program as well, you see that. Hold on a second. There you go. Then the main calls the print greeting and execution jumps to the function block, and print greeting calls the A greeting first, and the A greeting comes to this function block and returns back to the print greeting. Then print greeting calls the next one, so a print a comma, execution jumps to its function block, and once complete, then it returns to print greeting. The next one is print calling print and addressee, and execution jumps to the function block again. Here you go, and then print greeting, print and addressee finishes, completes its work. It's returning to print greeting, and the next we take the next line, which is the print a new line. Execution jumps to this function again, and we print a new line. And once the work is completed, we return to print greeting. Then this time we already realized that the curly bracket is closed. That means we finished with the running, so the block is finished, and we return to the main. And here we also have actually the return 0 and the closing curly bracket, meaning that now we can return to completely to the system. This is what happens, and this is what happened, and this is the description what you also saw. In each line, when a function returns, it picks up immediately from where it left off in the calling function. So if there were any statements after returns 0 or return, they would never be executed as well. And the last topic this time, understanding function declaration. In order for the compiler to recognize a function call when it sees it, it must already know about the function. In other words, it must already have processed the function statement's definition before it can process the call to that specific function. We have seen this behavior in all of programs up to this moment. In each program, we have defined the function, and then later in a program we called it. This behavior is somewhat limiting, since we may want to call a function from anywhere in our program. We don't want to get caught up in its relative position in the program and have to reshuffle the definitions of the functions just to make a compiler happy. The compiler is supposed to work for us, not the way around, so not we work for the compiler. C provides a way to declare a function so that the compiler knows just enough about the function to be able to process the code to the function before it actually processes the function definition. These are called the function declarations. they declare to the compiler the function name, the return type, and the parameter list only. Now, elsewhere, the function definition must exist not only with the same function name, return type, and the parameter list, but also to define the function block. In other words, the function signature in a function's declaration must match the function's definition as well as the function when it called. When function declarations differ from a function definition, the compiler error occurs. Now, this is actually frequent frustration, and then that's why, for example, we also have some ideas here. Function declarations are also called function prototypes, and it's better to call it in this way so that we don't get confused with function definition and function declaration. So function declaration is called then function prototype, and we will call them function prototype in the future as well. Now to do this, we can also move forward and run this part. Let's do it. We make a new file. Function declarations are called function prototypes, as we mentioned, and let's do it. So let's list our function prototypes. Okay, void print greeting and we can check this with char greeting char name semicolon again, and all I need this time is to basically just copy paste this. Sorry, oops, why? Okay, I don't know why. Nah, okay. So print a greeting this time. We can move away from this just with okay, parameter is only one. Then we need one more where we have one more parameter, an address C, right? And address C. Then char name. Then as for next is void print a comma. Oops, that was not my intention. My intention was copy paste simply. We can actually keep it in that way and print a new line. So it should be also working. New line. We can add void, we don't have to. If you want, you can do that. Should actually work in that way too. Let's try to run it this time. So I save it again. Again, now this time it's hello 7C, and we nearly finished with our stuff here. And yep, completely all right, working fine, no mistakes, no problems. Let's try to do that again here as well. Hopefully no problem. Hello 7, and there you go, all good, no mistakes, I'm fine. We can return now to our presentation and we can close it this time. So here you go. In hello 7C, we have rearranged the order of the function definitions in order to in this order, functions are defined in the order that they are called. And ordering such as this is sometimes called top-down implementation, since the functions that are called first also appear first in the program file. The main is called first, so that the function definition is at the top. Those that are called later appear later in the file. Print a new line is called last, and so shows up as the last function defined in the source file. This approach more closely matches the process of starting with a whole problem and breaking it down into smaller parts. Our previous programs are ordered in a bottom-up implementation, where we start reading the code from the bottom as it were. In those programs, main function appeared as last function defined in the source file. It doesn't matter if you take a top-down or a bottom-up approach. So basically, you can change the place of it. Here, actually, this is still a bottom-up approach. So let's do it. Let's put it here. And let's save it again. And let's try to run it. And there should be no mistake, no problems, as I expect. So there you go. You see, no mistakes, no problems. Yet again, let's compile it. Let's run it. No mistakes, no problems. So this is what is said. So in order for the compiler to be able to process functions in a top-down manner, function prototypes are required. Note that while any function prototype must appear before the function is called, the order they appear in is unimportant. All right, now we can summarize what we have just learned. In this chapter, we began with a very simple C program and explored C statements. We expanded and changed our program through the use of functions. We saw how to define functions, call them, and declare function prototypes. Lastly, we saw how we can structure our programs using top-down or bottom-up approach when implementing our program. Thinking about solving a problem in terms of breaking it down into smaller pieces and solving each of them through functions is an essential skill to be able to solve complex problems in any programming language. So in the next, we will begin to develop an understanding of data types. The data type determines how to interpret a value and what kind of manipulation we can do to that value. Thank you very much for your attention. We continue later on with chapter 3, so working with basic data types. Thank you. Bye-bye.